Okay, everybody, welcome to the second part of the third lecture. So, in the last lecture we were looking at the Angle Theorem, Engel's first theorem. And we had three parts, if you recall. And what we're going to do is actually point out, let me just write out what the theorem was again. Okay, so you don't have to go back and check. We want to let L be the algebra. And we had V rho was a non-zero finite dimensional representation of L such that rho x, which lives of course inside the linear endomorphisms, V is nilpotent. Okay, so L is a Lie algebra. We have a non-zero finite dimensional representation of L. Representation of L is a Lie algebra, obviously, such that this operator, clearly it's a representation, so by definition a representation is going to be a map from the Lie algebra into the linear maps on the vector space here itself, which, if you make a choice, the basis for V you can think of as the matrices of the dimension of the vector space. If this as a linear operator is nilpotent, so just be careful, we're using nilpotent in the sense of a nilpotent Lie algebra, and we're using nilpotent in the sense of an operator on a vector space, a linear operator on a vector space. And in this sense it just means, as you already know, it just means that if we apply it often enough, it will eventually be zero. Okay? So we're trying to say if we have this, if the representation lands our rho of x into the nilpotent operators, then first point was that there exists a V contained in V, non-zero, it's important of course, such that rho x by V is equal to 0 for all x non-value. Okay, it's an L invariant operator. This is actually going to be the vector space, the one-dimensional vector space spanned by this element is going to be invariant under L, which is to say it's a sub-representation. Okay, that's implied by this. But be careful, it's the same V for every x in the Lie algebra. That's the part that's not true. Because clearly, you see that if rho of x, because rho of x is a nilpotent operator, it'll have a kernel when you apply it. If it didn't have a kernel, it would be an isomorphism and it could never arrive at zero, so it wouldn't be nilpotent. So basically linear algebra. And then we have that there exists a basis of the, let me just be a little bit quicker with this, such that rho x is strictly upper triangle. Let me start using an actual triangle, a symbol of the triangle for T, because that's not the best triangle. Still a triangle, and the third consequence, there exists a notation by sub-representations such that 0 is the definition V0 lives in V1, and this is a strict equality. Okay, lives in So it just means that if you were at any point in this chain, this inclusions, that's basically what we mean by the filtration. It just means a sequence of vector subspaces which are included one in the other, and so on. It just means if you operate on any one of those by L, it's going to keep on bringing you down in this sort of ladder of inclusions. That's what we showed. So what we showed last week is that 1 implies 2 and 1 implies, 1 implies 3 and 1 implies plus 2. Okay. What we now want to show is the first guy. Okay. Which of course then implies that 2 and 3 are actually true. And that's what we're going to be concentrating on in this half of the lecture. And this one is a little bit more involved. The tools that we're using are still just basically linear algebra, but the argument is quite long. Okay? So, with that recalled, it's just before we do the prove a small side lemma, okay? Just to break things up because the proof is quite long. So if so this is in the general linear algebra, so we're just looking at the endomorphisms of the int out with the usual comment in a bracket. So if this is an important operator, then the adjoint action of x is an important operator on on G n. Yeah, of course we have no elements in it. So x is operating on, this just gets a bit confusing, so let's take a second to think about it. X operates on V, okay? It's an element of the general, it's an element of the linear transformations of V. But what we can do, because we have a Lie algebra structure on this space itself, is we can also let x act on the space in which it lives, using the adjoint. That's what the adjoint does. You take an element of the Lie algebra and then suddenly you turn the Lie algebra, you turn the element of the Lie algebra into an operator on that Lie algebra itself. So you sort of lift it up. And that, if you recall, also gave us a map that went from the Lie algebra into the linear operators on itself, into the general linear algebra. For any Lie algebra, it went from it gave us a map that went from the Lie algebra into the general linear group of the Lie algebra itself. So here we would be talking about the general linear group, not the general linear group of Lie. And remember, the kernel of this map would precisely the center. Okay, so let's prove it. And what we're saying here is that, look, if it's nilpotent as an operator on here, then it's nilpotent as an operator in here. So this is the left action to right action. That's where the L and the R, that's where the rotation comes from. How are they defined? This is the definition. We're going to use a colon as usual. This is the multiplication that's taking place inside here. It's the matrix multiplication. Okay, so be careful to. This is the matrix multiplication on left and right. Remember the adjoint is just in this, it's always going to be the x, y, the bracket. But what is the bracket in this case? So the bracket in this case is just the commutator bracket because we're living inside here. Okay. So this is precisely what it is. But we then write it like this, just because we find it convenient to use this notation for the next step. Maybe I should really write so. Denote. Because here we're really just introducing notation. Next, we should note that in terms of this notation, so let's assume an L to the n of, wait, this is not right. This is an X. Okay. L to the n of x is equal to 0 for n being the Newton degree. Okay? So this is just the number of times you need to multiply. You need to let x act to compose x, multiply x in order to get 0. So that clearly it will be 0. Yeah. So obviously just by definition, what you're going to get here is x to the n. So we see that L of x to the n y is equal to x to the n y, which is equal to 0, which is equal to 0 by definition. Because the product here is just composition, and this is just going to be, well, you let this act on an element of v, and then you let this guy act on an element of v, and it's 0. Same thing here, we also see on the right exactly the same argument. Okay, good. What we also note, though, is that L of x and R of y and some z. Wait, sorry, I just need x, I guess. No? Yes. X. What is this? Well, it says it's L of x and y x, which is equal to x, y, x. If this is equal to x, get this right now, this is equal to x, y, x. Okay. Because composition is associated. And then you get L, x, y. By x, which is equal to okay, so this is just the right multiplication here, and then this is the left multiplication acting on this element. This is L of x. Or x. So these two guys commute. Okay. Nothing very difficult going on here. Okay, so there's not enough space, so I'll just continue from here. Now, if these guys commute, then what happens is that, therefore, the adjoint of 2n x, which is equal to, remember the adjoint itself is just this. So if we're applying the adjoint 2 times, 2 to the n times, this is L to the x minus to the x minus or to the x to n, then we see that this is actually 0. So you can just expand this because these things commute. You can just use the binomial theorem that you know from childhood, and then you'll see that in the expansion of the binomial theorem, every L to the x or R to the x will have a power n or higher, at least one. And then this thing is 0 by assumption. Sorry, this thing is 0 by assumption that the degree of x is equal to n, which comes from the assumption in the first place that it was nilpotent. So the whole thing is 0. So if you've got some elements that lives inside the general linear group of a vector space, and it's nilpotent with respect to the action of the vector space, then when you look at the action of this element to the adjoint on GL of V itself, it will again be nilpotent. Okay? So nilpotency gives you nilpotency. And that's going to be a result that we'll use inside in the proof of part 1 of Engle's theorem to finish Engel's first theorem. So if you 1 second to read that. Okay, so back to the proof, and now we're going to do part 1. Okay, so we're going to use it by induction. That's something that happens, a tool that we're going to use quite often. So let's assume if the dimension L is equal to 1. Okay, so if our Lie algebra is at dimension 1, we want to show that if we have a representation of the Lie algebra on a vector space such that all of the elements of the Lie algebra in that bit are going to act nilpotently on that vector space, then we're always going to have an invariant element. Now what I want to do here, just for the use of notation, write x for rho x. Okay, it just makes our life a little bit easier. Hopefully it's not too confusing, but remember this. Okay? If you want to rewrite everything using rho, it makes it better for you, go for it. So if the dimension of, and the induction, maybe I should write this here as well, and also induction on the dimension of L. So there's two things to remember. Okay? Not the vector space we're acting on. The representation, we're just going to do all dimensions, finite dimensional representations in one go. Induction will be on the dimension of L. Okay? The dimension of the Lie algebra that we're looking at. Just try to keep this in mind to stop things getting confusing. So what we're going to do is start off from the first level of the induction. Okay, you could start off with the trivial Lie algebra 0, but that's not very difficult. That's obviously true. We're going to start our inductive process at 1. Okay. So if it's 1, and we know that x to the n is equal to 0, an element of this is the vector space, the general vector space, the vector space of general dimension upon which we're acting. So this is going to happen. Okay. But, which is to say it's going to be a nilpotent element inside here. Nilpotent element, a nilpotent matrix if you want to make a specific choice of basis. But then, of course, this implies that the kernel of x is non-zero. Because if it were 0, then it would be if the kernel of this was 0, then we'd have an isomorphism, which is dealing with finite dimensional vector spaces. And then this could never happen. I mean, for eventually, it has to kill things at every step. Because if it didn't, it would be an isomorphism, and no matter how many times you compose an isomorphism, it's still an isomorphism, i.e. it's never going to be 0. So clearly, because it's important, this happens, and then you just take, so we take any non-zero V and that V element in the kernel of X. Okay. So here you see that the difficult part of the theorem is not finding a V for any X. This is clear, because if it's for dimension 1, we're done. It's finding one which is 0 for every element of the Lie algebra at the same time. That's the difficulty inside it. And that's why Okay, so we're the first step of the inductive process done. Okay. Next, now let's assume this is, I guess, dimension. Now we're going to assume for the dimension is greater than 2.
Greater than or equal?
Greater than or equal to, thank you. So let's call this some K. No, K is the field, so let's call D. Okay. So let's assume that it's true for D, and then we want to show that it's true for D plus 1. So choose the least of algebra. Non-zero. So you got to ask, can we do such a thing? Maybe it's not completely obvious. First of all, will there exist a least sub-algebra? Remember, we had Lie algebras which were simple, which is to say that they had no ideals. Remember, an ideal is much stronger than being a Lie subalgebra. In fact, we always have Lie subalgebras. We've got the trivial one, of course. 0 is a Lie subalgebra. But we want something that's not trivial. How do you do that? Well, you just go back to the axioms. So let me just put another box over here and so if you just take the one-dimensional vector space band of this field, that's what it means. Why? Well, because x by x is equal to 0. The first axiom of the algebra. So this does actually make sense. The maximality, hopefully you can think about this yourselves. I mean, basically because it's a finite dimensional vector space, then your sub-algebras will have to have some dimension, non-trivial sub-algebras will have to have some dimension between one and the dimension of the thing itself, and one less than the dimension of the Lie algebra. And you just pick the top guy, pick something up top degree. And so put this as an exercise then. But it basically is just order of dimension. You don't need to take the span of the things, you don't need to take some intersections, some unions, nothing like this. You just need to think think about it in terms of the dimension. And you just pick the one of top dimension, and then of course you see that there can't be anything greater, because if there were, it would either be the whole thing, which doesn't count, or something between it, and that would contradict the maximality. Okay? And then put the hints here, so hints. It doesn't need to be unique, okay? Not like unique. There's no guarantee of uniqueness here, but that doesn't matter, we just want existence, not uniqueness. Alright. So now that we have this guy, let's introduce a new concept. Let me put a dot for this, okay? So, this is like a small lemma that I show. Okay, we're going to show that it's an ideal. That's not And remember, this is definitely going to use the fact that every element x is nilpotent inside here. Okay? Because this is definitely not true if you look at an arbitrary algebra and you want to look at some Lie subalgebra maximal degree, maximal dimension, then this will not happen. This is definitely not true. I mean, all you need to do is just think of it as simple Lie algebra, and of course this is totally wrong. So then I guess that tells you that you can't faithfully representing the algebra, simple Lie algebras as nilpotent elements is problematic. So what are we going to do this? Well, we're going to introduce, so consider n, which is defined to be x, an element of L, xi, contained in I. This is what we call the normalizer. So we don't know that I is an ideal, that's what we want to show. So what do we look for? We look for the largest subspace containing it such that I is an ideal in there. So such a thing has to make sense if we know, well, let's look at some properties of this thing. Okay. So and this will leave us an exercise again. This is Jacobian density. So now you'll see, well, I'll repeat this later on, but you see what we're going to do. Now that we know that I is in there, and we know that n is a subalgebra, this guy is maximal. It's the largest. There is no larger subalgebra containing I by assumption. So if it lives inside here, then we've got two choices. Either n is equal to I, or n is equal to L. But if n is equal to L by definition, that will actually tell us, by definition of the ideal, or the definition of n and the definition of an ideal, that will tell us that I is actually an ideal. And that's actually what we're going to try to do. So we just need to find one element in n that's not in I, and then we know it's an ideal. Okay. So let's do that. Okay, so let me. Yeah, we can get rid of this. I guess the dimension one is alright. So now, so the Lie algebra, I act on L. It's well defined. This is the Lie subalgebra, so we're letting it act. You can always let the algebra act on itself while the adjoint as I said before. So I is a sub-algebra of L, so you can restrict the representation and let this act on L itself. No problem. Now we're going to let it act on a quotient because the I acts on I is closed into this action because it's by assumption a Lie subalgebra. So that means we have a well-defined action of L through the adjoint on the quotient space, on the quotient Lie algebra. Okay? Or you can just, we're using add and giving us the embedding of add into the general linear group of this space. However, we see that because I acts nilpotently on the vector space, I lives inside in L. And we know that L acts nilpotently on the vector space by assumption. Now, that means that I must act on L nilpotently by the previous line. If it acts in the vector space, then it acts on the general linear group, so it will act on nilpotently, so it will act on subspaces. And then, of course, if it acts nilpotently on L, then it will act nilpotently on the quotient. Okay, so there's a bit there, but it's all linear algebra. So, but I guess really what I should write here is okay, we're assuming that it works for every dimension that's lower. Okay? And then we want to go up. So we're using starting dimension. The dimension of I of this subspace is smaller because it's a proper inclusion. Okay? And this should be maximum. Okay? So this is strictly contained inside an L, which means that now we can use the inductive hypothesis. We can use the fact that we've assumed that it holds for everything less. And remember, the inductive hypothesis holds true for its induction on the dimension L. So that means we're assuming that it works for every single representation for dimension less. Okay. Which was, remember, we looked at it when we looked at it for 1, we checked it for every single dimension. The argument was extremely easy, but it worked for every single representation V. So we're safe here to do this. So that means in particular for the action of I on this quotient, this representation, because I is less than the dimension of L, which is to say it's got dimension D or less, then it works on this representation. Therefore, there exists a, how would we write it? There exists a non-zero, write the coset like this, x plus I, an element of L over I. Sorry, here we're going after. Okay, I think everything is alright now. Yeah, that's right. Such that the adjoint action of x, sorry, not x, of let's call it y, it's an ideal. Which is of course equivalent to so we found an x in L actually, such that the adjoint action is contained inside an I. Right? And should I also write, of course, that this is equivalent to this. This means, of course, that x is not 1, right? Obviously. And this is going to be for 1. Which for all I do that x. Okay, just unpacking it. But what does this mean? Remember what n was? N was going to be those elements such that for every element of I, when we took the Lie bracket product, well, the commutator in this case because we're living inside the general linear group, that it landed back inside I. It was kind of going to be the largest thing, that it was the largest Lie subalgebra in which I was an ideal. Of which I was an ideal. But this is precisely the condition for this to happen. So that means that x is in n. Now, of course, we could say x is in I, so that's not really anything different, but it's not because, this is non-zero. What does that mean for it to be non-zero? For it to be non-zero, it means that x is not actually contained in I. So we've found an element. So we've shown, and this, of course, means that I is properly contained in n. Okay. So by using this argument, by taking this ideal, by quotienting, and then letting I act on it again, we've produced an element x in n that's not an I, which is to say we show that this is a proper conclusion. But remember that I was chosen to be maximum. I was chosen to be the largest piece of algebra. So then this implies this. So now this implies that n must be equal to L. Because it was maximum. So the fact that I was included in this gave us two choices. Either n is equal to I, or n is equal to everything. That means that n is equal to everything. Because of this magic element x that we found, which is not contained in I. And what does that mean? Well, that means that I is an ideal in L. Okay. So we found an ideal inside it. That's the first part of the proof, okay? So that's a good place to stop for 1 second and let you take all that in. Okay, so now we know that there exists an ideal inside in L, this ideal I. Now we're going to build on that to produce a sub-representation. Okay, so this is the part. Ideal in hand, let's move on. And this is, if you got confused by what was going on before, look, the only thing that we need is that we've used our assumptions about nilpotency together with the theorem that if an element acts nilpotency on the vector space, then it's a joint representation that acts nilpotently on the general linear group. The joint action gives a nilpotent element. We use that to construct an ideal. I contained in L. And in fact, let's remember the maximal subalgebra. There exists an ideal. In fact, it was just a maximal. Okay, so that's what we did. So if you got a bit confused, well, this is where we are. Let's go back to it. Okay, we don't need anything except this information. So vector space. We're defining a vector space W with these properties. And sorry, maximal proper. Okay, so it's definitely a proper inclusion. Which is to say, of course, that the dimension of I is less than the dimension of L. Clearly. So, we now claim this is not empty. Okay? The dimension is less. Why is that important? It's because we can now use the inductive assumption. We're assuming that it holds for everything less than the dimension of L. What does that mean? That means that there's going to exist, for any, the inductive hypothesis says that for any representation of I, the inductive assumption says that for any representation of I, remember the induction is on the dimension of L, not the vector space. It's assumed that it holds for every representation. The dimension of I is in where the inductive assumption holds. Hence, that means that for any representation, we have an element that's going to be killed by every element of I. Which is to say, there will exist a V inside here such that this holds. Okay? Same vector space with smaller Lie algebra, hence we can use the inductive hypothesis. Good. So this thing is non-zero. Non-empty, non-zero, I should say. Because clearly, that would be true if it was clearly zero was in there. Moreover, this doesn't use this yet, okay? We haven't used this yet. This is just from the inductive assumption. And now this is where we're going to use this guy here. Moreover, is a sub-representation. So, L. Okay. It's clearly a sub-representation of I because it just gives you zero. But it's a sub-representation of the larger by L. Why is that the case? Well, that's where we need this assumption here. To show that this new space we've introduced is a sub-representation. Because N Right, let me write this over here first. So N is in L, no, N is in I, X is in L, and V is in W. That's not so good. W should be in W. So we're now, what do we want to do? We want to show this guy here. This is a general element of L. What we want to show is that this thing here is still contained inside the W. That this guy lives in here. That's what we want to do. How do we know if something lives inside here? How do we know? Well, there's a condition for it, given in the definition. So we have to check the condition in the definition. What's the condition? The condition is that if you take any element of I and let it act on V, okay, all the elements here are just linear operators in your vector space V, so if you let them act on any, sorry, let me really make this a W because otherwise I think it's confusing. Okay, so if you take any W inside in the vector space V, something lives inside in W if all of the I's killed. So if we want to check that this thing is inside here, then all we need to do is check that it's killed by all the I's. So let's take a general element I inside here and let it act. Okay. But what is this? This is equal to X M W minus X M V. Why? Because the commutator, the lead, we're dealing inside in the general linear group of vector space. So that's where the commutator is. So if we take this, we know that it's just xn minus nx for composite, where the product is composition. But then that would cancel with this guy here, and we'll give you this. Okay, easy. Now we know that this guy here lives inside in I. Why? Well, that's where this thing comes in eventually. It's where we went to the trouble to prove it. Okay? It's an ideal. I is an ideal. So for any element m inside of our ideal I, any general element x, this guy is still going to be contained in I. What happens with any v in I? Well, it's by w. What happens with any w? Well, it's killed by definition. So this thing here goes to 0. But what we managed to do with this simple algebraic trick is we managed to switch these around. We switched them up to a cost, but the cost is actually 0, so it was for free. And now, this thing here, n acts in w is v as well. So this goes to 0. So this is equal to 0. So we took a general element w, we acted on it by a general element w, we acted on it by a general element x inside an I, and then we tested if it was in here. And the test, if it's in here, if it's 0, it's not, if it's not 0. But it's 0, therefore it's in there. Therefore, x w is an element of w. Therefore, L w is contained in w. It's a sub-representation. Which is what we're proving here. Okay. So this guy here is an L sub-representation. So let's move on to the third part. Let me take the definition. What should I? Yeah, let's take the definition of W and just put it over here. All right. Actually, we're not going. Well, let's leave that as well. So. So let's take that piece of information and put it down here. That means we can erase it over here. Alright. That brings us to point 3, final part. So now we note this is the algebra. Remember, this guy is an ideal inside here, so we can quotient by it. Acts on W. That's this guy here. Okay, because you've got an action of L and W. Okay? By so we produce an action of L like this, of L on W, the subalgebra defined like this. But we see that the subalgebra is the ideal I contained inside of W, or L, sorry, this acts as 0. This acts trivially, it acts as 0. So we actually have an action, a well-defined action of this on W. Okay, so by restricting the action of L and W. But now we see that the dimension of L over I is less than the dimension of L. Okay? Clearly, because remember, L was assumed to be non-zero. Let me put that up there. L was assumed to be, this idea that we're using to prove everything, that was assumed to be non-zero, which means that the dimension here is less. What does that mean? That means that we can take we can use our inductive hypothesis because the dimension of this is less. The inductive hypothesis only cares about the dimension of L, nothing to do with the dimension of the representations. It's assumed for every representation in one row. So the dimension of L is less than that. So that means, okay, that there exists a V inside of this subspace W, which of course is contained inside of V. Okay, so this V is actually in, small v is in big V, such that, L, every element of our Lie algebra L, wait a second, L, let's write this, x plus I, okay, is going to act on V to give us 0. What is this? Well, to see what this is, we go back and just remember what it's the restriction of this representation. Okay. We can define, well, that's why this is defined to be x operating on V. That's all I meant by this up here. This is the definition of this. Maybe I should write it up here. Whereby rho of x plus I operates on W is defined to be no, I said we're going to leave out the rows, so this is the definition of this action. I can remove these. The point here is that it's well defined because the I kills anything inside of W. So this is well defined. But we see that it's equal to 0, but it's actually equal to this. So remember, there are no cosets inside of the representation space. This is a genuine subspace, not a quotient space, a subspace of W. So for this to hold here, which holds by the induction assumption, that means that this has to be equal to 0. Okay? Which of course means that it's for every x in L, so that means that L operating on V is equal to 0. But that's precisely what we wanted. And therefore, and we're done. Okay. So long proof. But if you get this, it's very good. It's a good way to get into first big step, first proper step into Lie theory, to go through all of the details of this proof. Remember, there's nothing really going on except the axioms of the algebras and the basic stuff from previous lectures and some linear algebra. This was the first thing that we proved, the existence of this ideal, satisfying the properties that we have here. Then, the next step was to construct, so I guess we could call this, well, this was 1, and let's, we can get rid of that now. This was 2. We then used this to construct this L sub-representation upon which I acted trivially. And then finally we observed that if, for such an L, we actually carried representation of this smaller Lie algebra, because this was a proper inclusion. Okay. But that allowed us to bring the inductive hypothesis, the inductive assumption to bear, so there existed a V, and just by carefully looking at what the definition of this action was, which is to say this over there, we see that this is true. But that means that they're both for everything, so we follow V. And that's it. Okay. So that's the first of Engel's theorems proved. In the next lecture, we'll prove the second part of Engel's theorem. It's just basically a corollary of this, so it's a lot easier. And then, after this, we can move on to solvable Lie algebras, which are a generalization of nilpotent